Welcome everyone to our first video in our atomic theory unit, where we're going to look at early atomic theories. A few notes about this video and how to maybe you will learn best from these videos on atomic theory. Please make sure you're following along on the worksheets that I've provided you. There are some fill in the blanks. There are some areas that you're to add some key points. And as I've said before, those points that you're supposed to fill in on those worksheets are often the key points, just to keep you focused on kind of the key points of each area. It doesn't mean the other information isn't important, whether it's on the handout or whether it's something that I'm talking about in the video. Just learning the key points will not be enough to really learn the material. So simply put, our learning goal for this video is to understand the early theories brought forth by philosophers and some early scientists on the structure of matter. So let's really start at the beginning here. And in every culture in the world, philosophers, thinkers, just everyday people ask the question, what is matter made up of? Everything, there's all these things that are around us. What's everything made up of? What's the world made up of? And so you've probably come across the idea of four elements. And we've got a few versions of this on the screen here. On the left-hand side is actually four elements from the Cree First Nation in northern Canada. And here we have the familiar water, wind, fire, and rather than earth, they termed it rock because in northern Canada there is simply a lot of rock rather than kind of dirt and earth on the Canadian Shield. On the right-hand side here, we see the five elements that are connected to the geometric Platonic solids. We have earth, fire, air, water. And then we have the fifth one, the universe, which is kind of the nighttime sky with the stars and the constellations as well. And cultures throughout the world had very similar ideas about the different components that make up matter. And we'll get back to the idea of elements when we get to the periodic table. But our focus here is on atomic theory, and the first person who was credited with developing a really thorough atomic theory was a Greek philosopher, an early Greek philosopher by the name of Democritus. And even though everyone gives him credit, when you look into it a bit further, you see that his theories seem to have been based on his teacher, a philosopher by the name of Leucippus. And Democritus basically gets credit because his work survived several hundred years, and so if your written work survives, you usually get credit for things. So, what did Democritus say about atomic structure? And remember, he's a philosopher, so he's just thinking about this and reasoning about this rather than doing any sort of experiments or studying matter at all. He's just looking at the world around him and coming up with some ideas based upon that. So the first idea is simply saying that all matter, everything around us, is composed of atoms, which are something that are too small to be seen, and they can't be split down any further. So they're the smallest unit of matter. One of the really interesting parts of his theory is the idea that there's empty space between atoms. Think about how ingenious this is, because it turns out he is correct. But he comes up with this idea that there's this void, a vacuum in between atoms. And that's definitely not the way we see matter. Matter all around us looks to be continuous. We don't see the spaces between things. So that's a really neat idea he came up with there. And then he also said that atoms themselves are solid, but there's nothing inside an atom. So there's no internal structure. There are no components which make up the atom. So his work, though, and his influence did not last long. So, as revolutionary as Democritus's theory was, and it was revolutionary, it didn't last long because after Democritus, Greek philosophy really took hold, and along came Socrates, Plato, and Aristotle, kind of the big three of Greek philosophy. And it was Aristotle who really did a lot of damage to atomic theory because he did not accept the idea that matter was made up of individual atoms, and he really disliked the concept of the void, of a vacuum, of a space with nothing in it. And he put forth many arguments against Democritus's theory. And as a result, for thousands of years, atomic theory really took a back seat in terms of what was the popular scientific theories and scientific philosophies in Western Europe. Aristotle's views were very important to philosophy in Western Christianity. And as a result, atomic theory, once again, didn't make much movement. Although there were some philosophers who introduced the concept of atoms again, didn't really gain any traction. This doesn't mean that atomic theory was dead. In fact, in other areas of the world, philosophers reintroduced the idea of atomic theory independently from Democritus. Some of those philosophers was Al-Ghazali, who was an influential philosopher around the 1100s, early 1100s, in what is now present-day Iran. And Al-Ghazali spent a lot of his philosophical efforts rejecting and arguing against Aristotle. And so he put forth an atomic theory independent of Democritus. And then a few schools in Indian and Hindu philosophy also independently introduced as part of their philosophy the idea that matter at its base is made up of individual, indestructible particles. So let's move forward several hundred years here. So many of you will have heard of the scientific revolution. Okay, starting over. 3, 2, 1. So let's move forward several hundred years. Now, many of you will have heard of the scientific revolution, and but you may not be, you know it happened, but you may not be aware of kind of the order in which things occurred. So after the Renaissance in Europe in the 1400s, 1500s, there were several large and significant scientific advances, and those mainly surrounded mathematics and astronomy and physics. So Copernicus, Galileo, and then culminating in Newton and Leibniz discovering calculus. And this revolutionized the scientific world. And that really led to many different areas of science becoming more rigorous rather than pastimes or being closer to magic. Say, and chemistry is one of those. Chemistry, the word chemistry comes from the word alchemy, and alchemy was really chemistry before chemistry was a science. And about 100 years after the scientific revolution came a period known as the chemical revolution. And this is where there was a big jump and big advances in chemistry. And it occurred for a few different reasons. The first was the mathematical and the scientific groundwork that occurred in the 1600s. And the second was a technological advance, and that was the development of instruments that were incredibly precise relative to what they had previously. And this allowed for measurement. And as soon as you could begin to measure things more precisely, then you could start to quantify things. And this was in the chemical revolution. This is where chemists started to attach numbers and measurements and mathematics to chemistry, which really turned it into a hard science. Okay, pausing here to fix. Okay, starting in 3, 2. So there were several very important chemists during this period, and we will talk about many of them throughout the year. But for our purposes in atomic theory, we're really interested in John Dalton. And John Dalton's work in chemistry came as a direct result of Lavoisier's law of conservation of mass. So we talked about the law of conservation of mass in the chemical reaction unit, which governs our understanding of how chemical reactions occur and is the reason why we balance equations, because matter can be neither created nor lost in the process of a chemical reaction. And so grounding him in this work, John Dalton used the law of conservation of mass to develop an atomic theory. And most importantly, and the reason why we focus on John Dalton is because this was an atomic theory based upon experimental evidence. We'll come back to Dalton again later on in the year, but Dalton's work all had to do with chemical reactions and looking at the ratios in which chemicals react. During this time as well, many elements and compounds were discovered. You can see to the right of the screen here, here's Dalton's atomic symbols, and they're much more creative than the symbols we use now. It would be kind of fun to be able to use the Mercedes symbol for phosphorus still there, but we're left with boring letters. But so Dalton did a lot of work on elements. He looked at a lot of work on compounds. But Dalton's atomic theory was developed with this in mind. So his first point here simply said the chemical elements are all made up of atoms. His next point said that the atoms of an element are identical in their masses. So every atom of one element weighs the same. So this comes as a result of his work carrying out chemical reactions and measuring the reactants and products there. So through a lot of observations, and through all these observations, Dalton came up with this theory. So use the process of inductive reasoning to use a lot of observations to come up with a theory. So not only do atoms of the same element have identical masses, but if it is a different element, it will have a different mass. So atoms of different elements have different masses. And finally, when atoms combine, they always combine in whole number ratios. So you never get half or 2/3 or 1/16 of an atom. Atoms have to stay as whole because they are the building blocks of all matter. So the model that we use to describe Dalton's atomic theory is the billiard ball model. Now, Dalton didn't come up with this theory. He came up with his postulates, but it's a way of visualizing how he pictured the atoms. So once again, no change since Democritus. Atoms are still solid, featureless spheres. And in fact, the billiard ball model probably isn't the best way to view his model, because billiard balls are all the same size. A more accurate model would be using his model of every different element is a ball of a different size. So some are billiard balls, some are table tennis balls, some are tennis balls, some are bowling balls. And every different sport has a ball that's a different mass, and those are the different elements. The main idea here with Dalton's and this way we view his model is, once again, there's no internal structure to his atoms. So we will leave it here. This is the end of our kind of early atomic theory, and for about 100 years or so. Not too much work was done until we get to the atomic revolution in the late 1800s, early 1900s, with the discovery of radiation. So that's where we'll leave it for here, and we'll pick things up in the next video with our discovery of the electron in the late 1800s.